that wonderful? I promise we're not going to talk about proofs. No proofs. Okay? Basically, it's just the shape of what these molecules look like. That's it. So it's not too difficult. I sent everybody a chart of what I'm going to give you today, so you can use that to help you do the homework and just get that down. But anyway, I'm gonna show you like I didn't give that to you. Okay. All right. So Vesper theory, VSEPR. Theory. This basically talks about why they are shaped the way that they are. The electrons repel each other. So V stands for valence. And S stands for shell. What's the valence shell? The outside energy level. Good. E stands for electron. P stands for pair. R stands for repulsion. So the pair of electrons are going to repel one another and cause the shape that they're in. Okay? So let's go ahead and get right into it. First of all, let's talk about electron regions. Electron regions. These are the electrons around the central atom. We're only interested with the central atom. So, and a region is just an area of space, yeah? So, regions around the central atom. So, for example, if we have ammonia, NH3, remember how to draw the Lewis structure here? Count the valence electrons first, right? How many for nitrogen? Pull your periodic table out. 5, good. Hydrogen has 1, but there's 3 hydrogens, so we multiply that by 3. We have a total of 8 valence electrons. Then we ask, what's our central atom? Nitrogen. It's never hydrogen. This one's all by itself. So nitrogen is the central atom, and that's what we're interested in here. So we have H here. 2, 4, 6. We have 2 more. Goes around the nitrogen. Are we good? All right. So let's count the electron regions around this compound. Any ideas? 1 region, 2, 3, 4. And for this part, we're only going to deal with 4 regions. 4, 3, 2, I guess, or 1, but mostly 2, 3, and 4. Good? There are more than that, but if you want more, you take organic chemistry or a higher chemistry. So, yeah. So does everybody understand what electron regions are? Okay. All right, let's go ahead and get right into the different shapes. So I'm going to draw this table here. With the number of electron regions and then the electron geometry okay, I guess. Let's make that a little bit longer. Number of lone pair of electrons, and this right here is a lone pair. Why do we call it a lone pair? Because it's all alone. It's not being shared with anybody, right? Number of lone pairs of electrons. And then we'll talk about the molecular geometry. And then we'll give examples over here. And you can start on one page or whatever, whatever. I'm going to extend this until we're done. So I'm going to take 1, 2, 3, 4, 5, 6, 7, maybe 8 different examples. Okay. So whether you need 1 or 2 lines, that's up to you. Okay. You can draw small, you can draw larger. All right, so if we have one region of electron, and there's really only one molecule that I know of that only has one region, so I'm not going to really waste room on here to talk about it. This is the one. The hydrogen molecule, we only have one region of electrons right there. What shape is that? Looks like a line, right? Just a straight line. It's linear. So if it's a one region, it's always linear. There's no differences in electron geometry, molecular geometry, it's all the same, okay? But if we have 2 electron regions, it's also linear always. And we'll give 2 examples here. If we have if we have 0 lone pairs, then it's going to look like carbon dioxide. And if we draw the structure, in fact, it's going to look something like this, right? Any questions on how to draw the structure? I can do it again if you need me to. Okay? But this has 1, 2 regions. Even though it's a double bond, it's still the same area of space, right? So that double bond is considered just one region of space. But we have 2 regions around that central atom. Are we good? Does that make sense to everybody? Okay. And these electrons repel and push as far apart as they can, which makes it a line. What's the number of degrees between a line? 180 degrees. It's as far apart as it can get. Good? Okay, if we have 1 lone pair, it's still linear. In the example of O2, not O2, sorry, N2. So which one is the central atom here? Nitrogen or nitrogen? Yes. Pick one. Doesn't matter which. So if I pick the one on the left, there's my central atom. How many regions do I have around that central atom? 1, 2. Regions of electrons. You with me? So we have 2 regions of electrons, and one of them is a lone pair. But it's still a line. You with me? So no matter what it looks like, if there's 2 regions, it's going to be a line, no matter how many lone pairs we have. So if it's 1 or 2 regions, it's linear. That's nice, right? Pretty simple. Okay. Now let's go to 3 regions. 3 regions, the electron geometry is always going to be called trigonal planar. We'll talk about why we call it that. So if it has 0 regions, then the molecular geometry is also going to be called trigonal planar. And an example here is SO3. Looks like this. S is the central atom. How many regions do we have? 3. 0 bonded atoms, 0 lone pairs around the central atom. So that's it. What shape does this look like? Triangle, and it's all in the same plane. Hence we call it trigonal planar. Good? How many degrees is that? So 60, like for this is 60 right there, right? But the angle between these 2 regions is 120 degrees. So if we take 360 divided by 3, 120. And that's as far apart as it can get. If you try, let's say, so this is our 120 degrees. If I try moving it out a little bit, it makes these a little bit closer, right? So it's got to be on the same plane. I don't have my models here to show you, but my arms are good enough? Okay, sorry. Make sense so far? Okay. Next one, if we have 3 electron regions and 1 lone pair of electrons, then, well, if it's 3 regions, it's always going to be trigonal planar. The electron geometry is always going to be trigonal planar. Good? First of all, I didn't really talk about the difference here. What's the difference between electron geometry and molecular geometry? Electron geometry just worries about the electron regions. Doesn't care what's bonded to it or if anything's bonded to it. Okay? And the molecular geometry is worried about just what's bonded to it. So the atoms, if it has bonded atoms, that's all it worries about. Okay? So here we have 3 bonded atoms. That's 3 regions. That's trigonal planar, right? Okay, so if we have 1 region or 1 electron pair, then this is going to be like SO2, which looks like this. Good? And what does that look like? Here's a line, and that's what it looks like. It's just bent. So that's what we call it. The angle here is still 120 degrees. Can you make sense of these pictures, guys? Because if you can't, it's going to be really tough on you. If we need, I can pull up some images on Google to show you what these look like. But it's basically, so far, it's what it looks like. It is linear, it's on the same plane, so this is bent. Trigonal planar, it's pretty basic. Good?
Can you explain the difference between electron geometry and molecular geometry one more time?
So the electron geometry, so this one is the only one that's different so far. So let's use this one. So the electron geometry, we have one region of electrons here, one here, one here. So it's trigonal planar. Make sense? But for the molecular geometry, we just worry about the bonded atoms.
Okay.
And so it's bent.
Thank you.
No, thanks for asking. Are we good? Okay. On your worksheet from last time, there's a bunch of examples here. You can start with the Lewis structure if you want. I'm going to take a little break. Sorry about that. All right, any questions so far? Sorry about that pause. Okay. Let's go to, extend this down a little bit. If we have two regions, or sorry, three regions, two lone pairs, this is going to be like oxygen, which looks like this. Okay. So around one of those oxygens as our central atom, we have three regions and two lone pairs, yeah? What does this look like? If we look at the molecular geometry, the electron geometry is still trigonal planar. But what about the molecular geometry? What does it look like? If we just look at the bonds, linear. Do y'all see that? So here we see it as a line, right? Almost done for today. But we're going to practice, right? Yeah, let's spend some time practicing. But I think we need the whole time to practice. Any questions about 1, 2, 3 regions? Okay. Let's go to 4 regions. And the example we're going to do is methane, CH4, which looks like this. Well, that's what the structure looks like, right? I'm going to actually not draw that, sorry. I'm going to draw it how it really looks. Can you see that that's three-dimensional? Kind of like this is three-dimensional. No? I'll use a different color to help us to see it. Now do you see that? It's like a pyramid with a triangular base. Good? Oh, that's weird. Okay. So this is called, the electron geometry is tetrahedral. Why tetrahedral? You guys ever played Tetris? We have a block that looks like this, block that looks like this, like that, and like this. What do they all have in common? 4 cubes, right? That means tetra. Tetra is 4. Good? That's why we call it tetrahedral. And if we have, methane is 0 lone pairs, and so the molecular geometry is still tetrahedral. You see a pattern here, guys? if it's 0 lone pairs, the electron geometry and molecular geometry is the same. Good? But for four regions, the electron geometry is always going to be tetrahedral. Okay? Questions on that one? Can you all see what that is three-dimensionally?
Do you want us to draw it like three-dimensional, like a three-dimensional?
Yes, and it'll be better for you if you do. Okay? On the exam, and I say this every semester, and it seems like every semester nobody uses it, but I will have models over here, and you can come up, and I'll maybe have models back there too. You can come up and look at them during the exam, but it seems like no one ever does. I still will, just in case. Okay? But if you can draw these, then you don't really have to have the models. You can make sense of what it looks like. Okay? All right, let's go to the next one. If we have one lone pair and 4 regions, this is going to be like NH3. And we kind of drew the structure already up just before this. So it's going to look like this. So the way I do it is I draw the lone pair up top if it's like this. And I draw the hydrogen right here, 45 degrees-ish angles. That's not really 45, but 45 degree to the right, 45 degree to the left-ish with a wedge. Why do I draw a wedge? Yeah, it's poking out, right? When things are closest to us, like if you have one hand in front of you and one hand far away, you see more detail to the one in front, yeah? And then the one far away, it's not as detailed. It's kind of faded out. You follow? So we can see it's still, the electron geometry is still tetrahedral. Good? So what do we call the molecular geometry if we're just interested in that? What does it look like? A pyramid. So this is called a pyramid with a triangular base, trigonal pyramid. Let me use a different color here. Good? And if we have two lone pairs of electrons, like in water, H2O, oxygen's the central atom. I'm going to draw one hydrogen straight up, one hydrogen to the right and down, and then I have this lone pair going into the board or out of the board, this lone pair going into the board. You follow? So this is kind of like my there's not really a bond here, but it's a lone pair of electrons, right? You can kind of see that it's still tetrahedral, even though I drew that one kind of goofy. Okay.
And the angle degrees on it?
Oh yeah. Good. The angle between this is 109.5 degrees. 109.5. And I don't know that I'm going to test you on that, but just so you can kind of see what it looks like, right? All right, so if we just look at the bonded atoms here, so we know the electron geometry is still tetrahedral. What about the bonded atoms? What does that look like? Bent, yeah, that's it. The only difference between this bent and the other bent is the angle, right? This one's 109.5 degrees and the other one was 120 degrees. Next, if we have 3 lone pairs of electrons around the central atom, like in the case of HCl, we have Cl as the central atom. We have a lone pair there. We might call that hydrogen. And we have a lone pair there and a lone pair there. So the electron geometry is still tetrahedral. Sorry. And the molecular geometry is what? Linear. That's it. Good? Sorry. And I emailed you just before class a sheet with all this information on it. Okay? So why did we draw this? So that we kind of go through it together and make sense of it, yeah?
You didn't put like the genetic formula on there. Do you need to?
Genetic what?
On your email, it says total domains and then generic formula.
Yeah, the generic formula. It just, I just gave examples.
Okay.
So the generic formula might be something like AX3, right?
Okay, I see that now.
But, yeah, there might be a little bit more details on there. And there's a hybridization on there. We're not going to need to know that for this class, okay? If you're taking higher chemistry, then yeah, maybe, but good. That's it. Should we practice? Okay, so on the back side of this worksheet I gave you last time, does anybody need one? Yep.
Thank you.
Thank you.
Mhm. Mhm.
Thank you.
Yeah, you got it.
Thank you so
Mhm.
much.
Step 1, draw the Lewis structure. And I gave you a few steps to draw the Lewis structure, right? Okay. Any questions on how to do that? All right, step 2, count the electron regions. Around central atom. So we're only interested in the regions around the central atom. So if we have lone pairs around the outside atoms, then we don't worry about that, okay? And then step 3, use chart to determine the geometry. And I won't give you this chart on the exam, so you need to know this. Unless you can squeeze it on a little chart card, that little index card, right? But if you do that, you might not be able to put your polyatomic ions in there. So it might be good to get those polyatomic ions down, is what I'm suggesting. Anybody have those down all the way yet? Almost? Okay. Keep going. Get them down. All right, so let's go ahead and do SiO2. Count the valence electrons. That's how we draw the Lewis structure, right? Silicon has 4. Good. Oxygen has 6. There's 2 oxygens. We multiply that by 2. Add that together and we get 16 electrons. Okay. Which one is the central atom? We need to know this to draw the geometry. Silicon. We got 2 oxygens. Now I draw it this way to spread it out as far as I can. Why? Because that's what electrons want to be, as far apart as they can. Now you could draw the structure like this and that would be okay, but the geometry is probably going to be more like that. Who knows? We'll see. Okay. Okay, so we have 2, 4. That means we have 12 electrons left. They go around the oxygen. 2, 4, 6, 8, 10, 12. We used all of our electrons. Silicon doesn't have an octet, so what do? We keep sharing, right? So we're going to take 2 of these lone pair of electrons on the oxygen and make a double bond. And do the same thing on both of them. Now they all have octets. Are we good? Do we understand the octet? Okay. So step 1 is done. Step 2, count the electron regions around the central atom. How many do we have? Yeah, we just have 2. So what's the electron geometry? Linear. And the molecular geometry? Same thing, right? Because it's 2. If we look at our chart, it's always linear for 2. Good? What else do you want to do? Should we try CCl2O? Looks a little goofy. 3 different elements. Count the valence electrons. Am I going too quickly? Carbon has how many valence electrons? 4. Chlorine has how many? 7. There's 2 of those. And oxygen has 6. So that is 24 total. Did I count correctly? Okay. Which one's the central atom?
Carbon.
Carbon. Why isn't it oxygen?
Because it's the first one.
Goes first.
Yeah, it's the least electronegative element. What's the most electronegative element on the entire periodic table? Did we talk about this? The one that wants them the very most is fluorine.
Oh,
Okay? So the one furthest from fluorine, or guys, we don't even have to do this. We could look at our electronegativity chart that we're given on the exam, right? Giving you all the values, so you look for what one's the least value. So this is 3, or sorry, this is 2.5, this is 3, and this is 3.5. So carbon has the least, so that's the central atom. We have 2 chlorines, and it doesn't matter exactly where we put these. And there's the oxygen. We used how many so far?
6.
6. That means we have 18 left. Put them around oxygen. That's the most electronegative. 2, 4, 6, 8, 10, 12, 14, 16, 18. Are we good? Are we done? No. We need to share. Which one should we share with?
The oxygen?
Oxygen for a couple of reasons. Now, in reality, guys, on the Lewis structure, I don't care for this class. But try to make it as symmetric as you can. Why? Because that's more efficient. Okay? And another thing, just to bring it up here, oxygen has how many valence electrons before it's bonded to anything? 6, right? So if we take these 2 away and make a double bond there, oxygen has 1, 2, 3, 4, 5, 6 that originally came from it. Carbon has 1, 2, 3, 4 that originally came from it. And you can do the same thing on chlorine, and it has 7 that originally came from it. Sound good?
So just out of curiosity, you know, like on some of the things that we're doing, it's a rule to like put them in order. So in this specific case, when like these are drawn out, they're not placed in order based off of what's most electronegative. Like, would there be a scenario where it would be oxygen first and carbon last?
Like on fill in the electrons?
Or just like, for example, this specific question, would it ever be written where oxygen comes before carbon? So for example, it would be oxygen.
So like this?
No, like just the way that it's.
The script, just
Yeah.
the script, not that shape.
Oh, you mean right here?
Yeah,
So OCl2C?
yeah.
It's probably just what's more common, I don't know.
Oh, okay.
And for this class, don't need to worry about that. Okay. Because if we was to write this as its structure, it would probably be more like this, right? Because carbon's the central atom.
Mm-hmm.
We would see that. That would probably be the best way to draw it if we really cared, okay? But yeah, don't need to worry about that in this class. But great question. Anything else?
So the shape, or an angle on this one, would it be triangle?
Yeah, the electron geometry, what would it be? Is that what you're asking?
Yeah, wouldn't it be triangle, whatever, triangle?
Trigonal
Trigonal,
planar? Would that be what it is? How many regions do we have?
We have
3 regions and 0 lone pairs.
triangle,
Trigonal planar. What is the molecular geometry? They're both trigonal planar. Because there's no lone pair of electrons. Good? That's it. I mean, we can go over all of these. Is there any others you want to go over together? before you try practicing these on your own? 'Cause that's really where you're gonna need to get good at it, yeah?
Do you want with a negative charge?
Yeah. So which one do you want to do? BH4 minus or SO3 2 minus?
Let's do 3, 2, SO3, 2.
Okay, perfect. SO3 2 minus, so this is sulfate. So we're going to start the same way. Sulfur has how many? 6. Oxygen has also 6, but there's 3 of them. And what does this negative 2 tell us? We have 2 more electrons, right? 2 minus, 2 extra electrons. So that's a total of 26 electrons. Is that right? Yeah. Okay. Sulfur's the central atom. 3 oxygens. 2, 4, 6. We have 20 left. Am I going too fast? Okay. Then let's put them around the oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 2 left. They're going to go around the central atom. So if we was just interested in this structure, then we'd have to put brackets with a 2 minus charge, right? But that's not what we're doing. We want to know the geometry. We can care less about the bracket, right? Okay. So how many regions do we have around the central atom? 4 regions. We all count that? Okay. 1, 2, 3, 4 regions. That means the electron geometry is what? Tetrahedral. And the molecular geometry, we have 1 lone pair. Makes this what? What? Trigonal pyramid, yeah. And one thing I forgot to read on this, it says to draw it as the geometry of it. So here we go. We're going to draw the 3D shape of it. So I'm going to draw, and it doesn't matter where you put these guys. I just like, if I have 1 lone pair, I'm going to put it on top. And then I'm going to draw the oxygens out here. So here's my wedge. So practice drawing it like that. And at first, it's going to look a little bit clunky, and that's okay. Just practice, practice, practice.
So you don't have to like make actual pyramid, just this is fine.
Yeah. And when I took organic chemistry, the professor says, do all the practice. So I did, and I had these structures all over. I feel like it was all over my house, but not quite. But if you do that, you're going to get good at it. Okay? So if we were to do that on this one, we would draw it like this. I'd probably draw the oxygen up here, something like that, so it looks more symmetrical. And notice I didn't draw the extra dots on the oxygens or the chlorines. Okay. We're just interested in the geometry. We're not going to draw all the dots. Is that okay? If you want to, you can.
So Professor, with the tetrahedral, that's when we do the brackets. It's the only one where we do the brackets.
This right here,
Yeah.
we do brackets only for the Lewis structure for polyatomic ions. Why? Because we've got to just denote that it has a charge. Good?
Thank you.
Any others before I turn you loose on this?
Am I reading it wrong, or is it like sulfur only has 5 right there, or is that?
Oh, you mean like right here, 1, 2, 3, 4, 5?
Yeah.
You're right, it does. And so an oxygen has 7 and it's supposed to have 6, right? But we have 2 extra electrons. Who's going to take them? The oxygens would rather have them because they're more electronegative, right? And it's more electronegative than that one, so it's going to take it. They still have octets, so yeah. The ones that you have to worry about, like how I showed you there, are the ones that are tricky. You might can draw them a couple different ways, which is the best way. That's really the only time you have to worry about that. Good? Great question. Okay, go ahead and try some of these. And then I will put the answers up here so you can see if you're doing them yet. Right? Good? Any questions, let me know.
When, right, nitrogen, 5, hydrogen only has 1.
It's 1, but there's 3 of them, so 1 multiply 3.
Oh, okay,
So that's 3 plus 5 is
8, okay, so that just makes it complete, okay, all
Okay.
right, thank you.
good. So, no, that's good. If you ever get an odd number, you know you counted it wrong.
Yeah.
So that's what you, yeah. That's
So is that correct?
So, 2, 6, 8. Plus right here. Oh, you did.
Yes.
Yeah, yeah, yeah. Okay, yeah, okay, perfect. So you got 1, 2, 3, 4, 6, 8, 10, 12. That is good, except for this one doesn't have an octet, right?
Okay, so it'd have to be a double bond, or
Yeah.
double covalent.
That's right. Mm-hmm.
But is this correct?
But yeah, that wouldn't change, right?
Yeah. Okay.
Uh-huh. So trigonal planar fluid.
So how do you know which one goes with it again?
It's, so on the periodic table, periodic table? This is the most electronegative. The one furthest from that is the essential atom. So, but it's never gonna be hydrogen, never.
Okay.
Do you understand why?
Yeah.
Okay. So, in this case, it's carbon versus oxygen.
Gotcha.
That one is.
Thank you.
Okay, just, like, I did some random ones, I just have a question, I put this one right?
So the way you have it here, we have 2, 4, 6, 8, 10.
Oh, so I have
This-
one extra.
Yeah, so we need to take one of these off to make it not a double bond. So just one of them should only one of them needs to have a double bond.
Okay, so like.
Does that make sense?
Yeah, so then I'd like take this one off and then just put 2.
That's right. So
But it
only,
would still be the same one in there.
yes,
Okay.
uh-huh,
I just miscounted them.
okay.
So for the milk marker geometry, it would be bent, right, because of the 2?
Well, there's 1, 2, 3, 4 regions.
Oh,
So we look at 4 regions
Yeah.
and there's 1 lone pair, so that's gonna be trigonal pyramid.
oh, it goes by pair. Sorry. Okay, that makes sense.
Yeah, yeah.
Yeah, okay, thank
We good?
Yeah, thank you.
I have a question.
Yeah.
So like for this one, NO, it's a nitrogen, oxygen, and then fluorine,
Mm-hmm.
right? So fluorine would be the center, right, because it's the most electronegative?
We want the least electronegative to
Because
be
all
the
that's right,
center.
or else it'll pull all the
Uh-huh.
electrons. So then in this case, wait, so, but they're on the same, oh no,
So
it'd be nitrogen.
that is the least electronegative. But, so I'm doing NOF on the board up here. Generally, the least electronegative is nitrogen, is that okay?
Yeah.
Okay. And so this one's one of those ones that's a little tricky. So to know how to do this one right, let's just try it. Let's put N in the center, because it's the least electronegative, right? 2, 4, so let's count these. There's 5, 6, and 7. That's a total of 13, 18, okay? So 2, 4, we have 14, 2, 4, 6, 8, 10, 12, 14, okay? And then we might share some from oxygen because it's not as electronegative as, oh goodness, not as electronegative as the fluorine. So something like that. And then we count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So they're all good, right? If we tried it the way that it was written, oxygen in the center, then nitrogen, then fluorine, 2, 4, 6, 8, 10, 14, 16, 18. Was that all there was? 2, 4, 6, 8, 10, 12, 14, 16, 18, right there, okay? And then, of course, we will have to share 2, 4, 6, 8, 10, 12, 14, 16, yeah. And so now they all have an octet. Now if we count, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Which one's more favorable? The top one. Does that make sense? But again, if we just follow that, the least electronegative, that's the one. Good? Is that what my answer key says? Yeah, okay. Did that make sense?
Yeah, I thought it was gonna be linear, not bent.
And that's why we just go
Have
through
to
the
just
whole
draw
thing. And we count the regions. And 1, 2, 3 regions. And so it looks like this. Right? So it's bent.
That's bent and linear?
For which one? NOF?
Yeah.
Trigonal.
So the electron geometry is trigonal planar because there's 3 regions,
Oh,
right?
yeah.
And then it's bent because there's only 2 bonded atoms. And then there's one right here causing them to bend down.
Even though there's a double
Yeah, the double bond doesn't matter, it's still one region,
Okay.
cause it's in the same area, right?
So the total 2 regions then?
One right here, two right here, and you got the lone pair. That's a region of electrons around the central atom.
Even though it's not connected to anything but.
That's right.
central.
Mhm. So if you look on our chart, so we're talking about number of regions, or sorry, number of lone pairs. So we have 3 regions right here and 1 lone pair. That's bent.
Okay,
Good?
thank you.
Mhm.
So basically, everything attached to the central region.
What? Yeah, every,
Everything attached to that central.
that's right. And we only count the ones around the central atom.
Okay. Copy. Oh, my wife said between 5 and 6 on Saturday. A little
Okay.
earlier. Is that better?
Yeah, that's fine. Yeah, put that in my,
We just finished with a tutor.
so you want it down at Walmart?
Is that good?
Yeah.
It's close to Tony Burgers.
What?
Nothing, we got a burger thing going. Like, everywhere we go, we're just trying to get a burger.
Okay.
Cheat on the diet kind of thing.
Good.
Tony Burgers right out there.
Nice.
It's so expensive.
Yeah.
It's super expensive.
Tony Burgers?
Tony Burgers?
They're super expensive. Like one time I took my stupid sister-in-law out and she brought her like 1,000 kids and I thought it was gonna be like $30. And it was like over $100.
No, it was just the 2 of us.
For burgers, I know, but then I felt like it was already there.
Yeah.
Yeah.
See, that's the thing, when you like have a diet, and then like you're regimented about what you eat.
Wait, you want a burger only diet?
My burger is like outside the diet, so like we have like
Oh,
a
I
disciplined
see.
diet, and then like, so when you go out to eat, it's like, okay, this isn't like every day, like a lot of people, they eat out all the time, you know, like,
Yeah.
oh, it's dinner time, what should we get? Should we order
Yeah.
out, like,
Sorry.
buy my meals?
Root
Get it ahead of
structures, I feel
time,
like I'm good
you know,
up
7
until I
days a
have
week,
to
but
share
then, like,
electrons,
on
and then I
weekends,
don't
like,
know.
once or twice a
Oh,
week,
so you don't like sharing, huh?
No, I don't. I don't know who to take like electrons from.
Okay, so
Yeah.
can I use your periodic table again?
In a.
Which one?
This one.
Okay, 1, 6, 7. Okay, good. All right. So here's your first mistake.
Okay.
Hydrogen. So these guys, everybody tries to follow these guys, right? What one does hydrogen want to follow? It's the closest one. So this is 1, this is 2. That's the closest one to hydrogen. Follow?
That's crazy.
So it only wants 2 valence electrons. So, sorry, it only wants 2 electrons. So that's the octet for oxygen is just 2. Here you put 2, 4, 6. Way too many.
Okay.
So we're not gonna give it to them ever.
Okay, so hydrogen is
Yeah, only wants 2.
okay.
Okay? So 2, 4, 6, 8, 10, 12, 14. And there you go, they all have an octet. Does that make sense?
I think so.
Okay, so 2, 4, 6, 8, 2, 4, 6, 8, and this one has 2, so it's good. So that's the only exception.
Because normally they all want 8, right?
Yeah, and hydrogen's the only one that wants 2.
Okay. Okay.
Because this oxygen wants that.
Mhm.
Chlorine wants 8, just like all these, right?
Okay.
Yeah. And if we look at this, this is correct because we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7.
Mhm. Okay. Okay.
Makes sense?
Yeah, that makes sense. Thank you.
Yeah, you bet.
So, I just think that genetically, you
Mhm.
have to eat
This,
good
right?
for
So
your genetics.
sulfur has 6,
Mm-hmm.
oxygen has
Like some
6,
people,
chlorine times 2, it's got 7, so it's 14, so it should have 26
farming in their
electrons.
DNA.
Good.
How do I determine when they're the same? How do I determine which one's essential?
Okay. So it's not the same number of valence electrons. It's the one that's
On the periodic table, like, would it be closer to the top?
we have.
Yes, the periodic.
You have the periodic table from the exam.
Type A or type B.
Okay. I'm just trying to see because this. Alright. Let's see. I might.
Okay, yeah, yeah.
I feel like I'm a pretty big fan because my husband's a huge UFC fan, like huge fan. And we're trying to find someone who's
The least electronegative element is the periodic table, on the periodic table. So this one is the most. So oxygen is 3.5, sulfur is 2.5.
Okay, so I would just go off of the
Yeah.
table.
Or sorry, chlorine is 3.
My friend that's in the
So
UFC right now.
this one's the least.
This is a tool, I was just trying to figure out, I was like, going off of the valence electron, so I would put the, so, okay. So I'll put the sulfur centrally, right? And then I'd need to bond
All of the rest to it.
oxygen, right? And then that's, so this is 1, 2, 3, 4, right? So I get rid of 4 of these, so I'd have 22
So that was just us
left.
last week. And then one of his fighters won.
Oh, but I'd have another one,
Mm-hmm.
We,
so, that's another, so I'm down to 20,
no, court.
Good.
right?
Court maybe.
Mm-hmm.
And then
And our sons are the same age.
there's 6 here, so 1, 2, 3, 4. That doesn't make sense to me.
What doesn't?
Like 1, 2, 3, 4, 5, 6. Like, you know what I'm saying?
So we got 2, so 1 or 2, 4, 6. It has those 2 also.
So that's 7, 8 octet.
Yeah,
Okay.
but we only used an extra 6, so that's 14.
The reason I asked is
And then here we're gonna use 2, 4, 6, 2, 4, 6. That's 12. We have 2 more.
And that's up there. And that's because we have a lone pair and 1, 2, 3, 4 regions.
So 4 regions, 1 lone pair.
So it's tetrahedral.
It's one in Sandy,
you know what?
So that's the EG.
I feel like it was that UFC gym.
And the molecular geometry would be
Yes. Yes.
That would be,
UFC gyms outside of
that's not
Vegas
the pyramid.
are not
it
too
is the pyramid.
Is it because it's only got 3 limbs?
So I use your pencil then. So if we draw it, so this is the Lewis structure. So if we draw the,
UFC gyms is
so we got sulfur, put the lone pair right there,
Mm-hmm.
and then we can have chlorine,
Which is fine.
because we know it's tetrahedral, so we're gonna draw it like this, right? Oops, sorry, that was a chlorine. And so there it is,
Oh, this is your
I
instrument?
see.
trigonal
Can I have
pyramid.
this though?
Because the molecular geometry deals with just the bonded atoms.
So just the bonds, so just these, I refer to them as limbs, but just
Yeah.
those bonds,
Uh-huh.
that's what I'm looking at.
For the molecular.
The molecular,
Yes.
okay,
Mhm.
okay, thank you.
Yep, you got it. Do we have any other questions? You wanna go over any others? Oh, I just lost my signal.
My thing is just we're getting not the regions, but the name of the shape down. So we're gonna have to memorize the shape.
Just
If we draw it right.
know what they are,
Yeah,
yeah.
you know what I mean, but if I like draw it properly, I mean, that's, you know, oh, this one's a tetrahedron and this one's a bent and, you know, but if I draw it properly and connect, you know, everything, that's,
Yeah. If it's properly.
yeah, if it's proper, you know, if I do your formula, right? The number of electrons, you know.
So, the best way to get this, guys, is just to do it and do it and do it until you're just good at it. Same with everything, right?
But if you just follow this list, that's all, that will give you the answer basically,
Yeah.
right? So that's all you really need to know, so like for example.
It's all you need to know, so make sure you know it by the time you get to the exam so that you have it there, right? And if you don't have it there, then you better put it on that little index card, whatever you don't have.
Okay. Yeah, cause the linears I can't really remember, the ones that I struggle with are the trigonal,
Mhm.
planar, whatever.
And the
then
tetrahedral, yeah.
But,
Anything
like,
else?
You don't need to draw it out, right? So if you.
All right, you're welcome to go. Don't stay here just because it's not time.
So like
If you're good, you're good.
4 regions.
So you're saying, like, but if we draw it properly, we don't have to like label it, like linear bend, you know, we don't have to label it.
No, it depends on what the question asks.
So there will be the questions that will have the drawing and we have to figure it out.
Or it'll give you the chemical formula like this and say, what's the geometry?
The only thing that I just struggle with is just drawing it, because sometimes I'm just not putting it in the right places, but I can figure out like, okay, how many, like regions it has, which I check, and then I'm like, okay, it has 4, and then it has like 1, lone pair,
Mm-hmm.
so then I know it's a tetrahedral triangular pyramid, right?
Yeah.
I don't need to like draw it out to know that.
Yeah, if you have it memorized right here, yeah, you don't have to draw it.
Okay, 'cause I just.
You don't?
You don't have to draw it three-dimensionally.
Oh,
You just
I
have to
mean-
know the loose structure, right?
The reason I say draw it three-dimensional is so that you understand what it looks like.
yeah, okay.
Because if you know what it looks like, you have to have less up here, you know?
I don't mind doing that.
Right.
Thank you.
Yeah.
Yeah, our daughter, she was like the one, she was like